Okay, so this is a lecture about Hamiltonian learning. Maybe before I start, let me I think you asked a very important question in my first lecture about this transformation of observables. Let me maybe emphasize this once more because I think I didn't do such a great job in explaining it. But you know, the point is just if you have some observables like this swap operator that I showed, which is as these eigenstates phi plus phi minus phi plus psi minus. Right, so the point is just, if these states are entangled states, you cannot see them directly in an experiment. We always make these snapshots and then we see zeros at once. So what you need to do is you need to, apply a unitary transformation on this thing, such that if you have here a V and a V dagger everywhere, that this sort of sends these things into products that you can see in the experiment. Okay, so by measuring the trace of this thing in the state, this is actually something now you can measure it, right? As soon as you see a zero, you assign the corresponding eigenvalue. And this transformation, you apply it, of course, on the density matrix. Okay, so this is just very basic and very important, like how we measure anything in all of this programmable bottom simulators. Okay, so about Hamiltonian learning, basically the thing is, all of us all the time, solve this equation, right? This is our everyday life. And the Schrödinger equation, usually what you do is you start with the Hamiltonian and you compute eigenstates of the Hamiltonian, or you compute its time dynamics. It's very interesting that actually just recently people started to ask the inverse question, like given a state, what is the Hamiltonian that produced this thing? This is what this lecture is about. And what I have in mind is programmable quantum simulators. So, in quantum simulation, we have a Hamiltonian, and computational physics takes this Hamiltonian, puts it on a computer, but sometimes this is too difficult. So we design a special purpose quantum device that mimics the properties of the Hamiltonian. And when we are successful, we can just measure the stuff we're interested in instead of computing them. That's the idea of quantum simulation. So you start with a Hamiltonian, you prepare a state, and then you study properties of that state, right? That's what we always do. And we have two kind of directions that we can go. We can study maybe eigenstates, like ground states of this Hamiltonian, or more generally, we will have a thermal state. Or what's actually more natural in these systems is time dynamics. This is even more easily doable in many of these programmable quantum simulators. And in this lecture here, this lecture is about the inverse problem. So given a state, you have in your lab, you have there a state. What was the Hamiltonian that produced this state? Like you have a state e to the minus beta h, and you only can do measurements on that state. Can you find out what h is? Or you do time evolution of the state. Imagine you have experimental friends in the lab which do this. They time evolve with the Hamiltonian, and after some time you are allowed to do some measurements. Can you tell them with which Hamiltonian they time evolve? This is the problem of Hamiltonian learning. And you can of course ask, why is this interesting? Well, first of all, you can use this to verify quantum simulation experiments, right? So experimentalists do their best to design a specific Hamiltonian. If this is possible from local measurements, if you can learn what a Hamiltonian is and tell them, then you can tell them that they did the right thing, that the thing works. It's a kind of a procedure. You can use it to study fundamental physics. In the last talk in the end, I mentioned this entanglement Hamiltonian, right? So if you can learn this, you can do fundamental things. And it is also, maybe I make some comments about this, you can use it to use it as a tool to design stuff, to design gates or Hamiltonians with interesting properties. Actually, a new direction where I'm doing currently some work on. We can discuss this. So let's for the moment focus on equilibrium states. Can I just, sorry, I approximately have time until like.
You should give yourself at least an hour.
Oh, okay.
The length originally.
Okay, you just tell me that. Right. So let's take the following thing. You take your favorite antibody Hamiltonian, whatever it is, you know, and let's say you take a system size that you can diagonalize 15 qubits or whatever. You completely diagonalize it, you compute its spectrum, and then let's say select a random eigenstate. You pick randomly one eigenstate out of the spectrum, and this eigenstate you send to me via email. Say. Question: can I tell you back which Hamiltonian you diagonalized from having access to a single eigenstate? Who thinks this is possible? Not? Okay. Yeah, usually, yeah. Of course not, right? It's the usual reaction, right?
Like, is it in general? I don't think it's the inverse product is 1-to-1, right? It could be the same state as multiple.
Exactly, yeah, yeah. So that's right. So the usually people start to throw tomatoes at you if you make this statement. Why? Because exactly we can come up with a lot of counterexamples. One counterexample is, let's take this Hamiltonian. You can also look about these things, like there is a talk from Lindbladian on YouTube which I can recommend, where these things are discussed very nicely. Let's take just the Hamiltonian that is a sum over all sigma c's with a minus in front. We all know what the ground state of this Hamiltonian is. It's the maximally polarized state, right? And now we can change this Hamiltonian. We can put some coefficients in front of these sigma c's. As long as these guys are positive, this will still be the ground state, right? So this is definitely not a Hamiltonian that has a unique ground state. But of course, this Hamiltonian is not very interesting, right? Because this state is an uncorrelated state. It has no entanglement, like what I discussed about in the last lecture. So the reason why this happens here is that the state factorizes into a tensor product of single particle states, and in a way, each particle has its own parent Hamiltonian, which you can, of course, arbitrarily rescale. But usually, eigenstates of our Hamiltonians we are interested in, they are intact, right? So even though this is a perfect counterexample, maybe it's not very relevant for the stuff we are asking, right? So maybe we are okay. The second counterexample is that people come up with. Let's just expand the Hamiltonian in its eigenbasis and change these eigenenergies, right? You get a new Hamiltonian that has exactly the same eigenstates. Imagine we have a spectrum and we take the ground state and we just, enlarge the gap, right? By adding a projector that's orthogonal to the ground state. But it turns out when you do this, your Hamiltonian becomes extremely non-local. And projectors are very non-local operators. But all Hamiltonians that we are used to in many-body physics, they are local, like think about Hubbard models or so on. They have geometrically local interactions. So this is also not a very interesting counterexample. And it turns out that if you make some restrictions, in terms of locality, if your Hamiltonian is a sum of terms that are geometrically local, turns out it works. You can do this, and it's unique. You can uniquely recover a Hamiltonian from a single eigenstate. There have been many papers have been written about this. One of the first papers had the title, "Does a single eigenstate encode the full Hamiltonian?" And a month afterwards, I think there was a paper determining the local Hamiltonian from a single eigenstate. Actually, the argument of the first paper, why a single eigenstate includes the Hamiltonian, was the following. Remember the last statement that I made in the last talk. If you take some highly excited eigenstate, psi k, and you trace out a subsystem A, right? And you look at the reduced density matrix, rho A of the subsystem, Eigenstate thermalization hypothesis tells us that this is 1 over c e to the minus beta HA, where HA is the system Hamiltonian projected on the subsystem. Yeah, and voila, there is your Hamiltonian. Right? So a single eigenstate somehow contains the information about the Hamiltonian, where it comes from. So this is one statement that where sort of why I got very interested in Hamiltonian learning. And there is a second thing, what I like about it, it's so simple, it's so easily doable. Hamiltonian learning codes can be written in 5 minutes. You know, every one of you can do this in an hour. I will show you how this is done. So I thought a little bit about for this lecture, what's the best way of presenting these things such that you also get sort of the gist of this, what happens here. And I found maybe an example that is somehow in between. It's not completely trivial, you know, but it's a nice way of illustrating this. And I would, you know, demonstrate these different methods for Hamiltonian learning on this one example. Actually, this example came out from a discussion that I had with Matthias Treuer at some point. Matthias Treuer was asking me that I was explaining to him Hamiltonian learning, and he was asking me the following question. Take a state that dimerizes, a 1D state, a 1D chain of spin 1/2 particles, where the pairs form dimers. Okay? So a dimerized state, each pair of particles is in a singlet state. Can you write down a Hamiltonian that has this thing as a ground state? And actually, this is a bit difficult because it's a little bit similar to our maximally polarized state, right? This example I just showed. It's almost a product state, right? It's a product of dimers. So we cannot expect that this is uniquely true here. And indeed, you can write down Hamiltonians that trivially have this state as a ground state. What you do is you take a Heisenberg model, which has different couplings for nearest and for the nearest neighbors, depending if you have an odd bond or an even bond. Right, so if you have a J coupling here and a J prime coupling here, if you put J prime to 0, then actually, you know, the scalar product of two spins Si plus 1, which is, you know, xi plus 1 plus yi plus 1 plus ci plus 1. This thing does have the ground state of this thing is the spin singlet state, right? So there is a trivial answer. But you can ask a more interesting question. And the more interesting question is there a translation of the invariant Hamiltonian that dimerizes in the ground state? So here we have alternating couplings, and it's trivial. But is there something that has the same couplings everywhere throughout the whole chain, which has as a ground state a dimer state? Does anybody have an idea? Does anybody know this? Oh, okay. Actually, you can search this. There is some literature. This is known. It's called the Mashunta-Gauss chain. What you do is this Mashunta-Gauss chain sort of minimizes the total spin on 3 consecutive sides. You add up I plus 1, I plus 2, square it, and sort of the minimum of this, actually the minimum of this on 3 spins, what you find is that 2 form a singlet and 1 factors out. And if you sum over this over all pairs of 3 particles, then you get this dimer state. You can multiply this thing out, and what you get is you have a coupling J for nearest neighbors and a coupling J half for next nearest neighbors. This Hamiltonian has a dimer state and a ground state. It's a kind of frustrated system, right? This is an antiferromagnetic coupling. So nearest neighbors want to be antiparallel, but next nearest neighbors also want to be antiparallel with a different coupling. So it's a kind of frustration. And the system responds to that with that dimer state. So the question I want to ask in this lecture, can we learn, I give you this dimer state, can you recover this Mashunta-Gauss Hamiltonian? That's what I want to discuss with you. And the plan is to discuss three different methods of Hamiltonian learning. And all three, let's see if they give us this machine question. All right. So let's discuss method one. I call it the method of G and Rama. So you can find this paper. I don't have the reference. It's a quantum paper, like in quantum. G and Rana, they both had been at Stanford at the time. I think if you Google G and Rana Hamiltonian, you can find this. And their idea was the following. So we have a state, right? And we want to find a Hamiltonian that has that state as an eigenstate. What they said, let's do the following. You write down an ansatz for your Hamiltonian, which is, you know, just some linear combination of local operators. So you have an ansatz class of operators hi. So they form your ansatz. Okay, and now our task is to find the coupling coefficients alpha I. And what these guys proposed is simply minimize the variance of the Hamiltonian in your state. If the variance is 0, this state must be an eigenstate of the Hamiltonian. Right? So you have, like you take the state, you do your ansatz Hamiltonian squared, right? And then you subtract the expectation value of this ansatz Hamiltonian, and you square this expectation value, and this you try to minimize. Yeah. Now the fun thing is that this minimization has a solution, a very easy one. Let's plug in this ansatz into this equation. Actually, if you take this ansatz, plug it in here, what you get is sum over all i's and j's. Alpha I, alpha j, hi, hj, minus hi, hj. Does everybody see that? I just took this ansatz and plugged it into this equation. If you square it with alpha I, alpha j, hi, hj, this is the first expectation value, and here you get the product of the expectation values. And this you want to minimize. But this thing can be written as actually a matrix equation, alpha transpose times a matrix G times alpha, where this G, you know, the matrix elements of G are exactly this connected correlation functions of your local energy densities. Hi, hj minus hi, hj. And which alpha minimizes this equation? Well, the eigenvector to the smallest eigenvalue, right? So what you do is, this is what I meant, this is so easy. You construct this correlation matrix, this gives you this matrix G, you diagonalize it, and the solution is the smallest eigenvector. That's done, that's Hamiltonian learning. All you have to do is calculate this thing. And in experiments, it's also doable, right? It's just a connected correlation function of local energy densities. So this is what we have to do here. Let's do this for this example.
This always varies the direct set of platforms.
Yeah.
Yeah, that's the answer.
Okay. Yeah, it's unbelievably easy. Yeah. It's of course you only learn a Hamiltonian to which size the eigenstate is an eigenstate, right? It doesn't guarantee you it. There are also methods where you can guarantee that psi is the ground state. Actually, I don't think that I will have time discussing that, but let's see. Right, but let's do this for, so we have this timer state and we have to write down an ansatz, okay? And I want to enforce translational invariance, right? I don't want to learn this trivial solution here. So my ansatz that I'm going to write down is an alpha 1, and then I have here si plus 1, like nearest neighbor countries. Okay, and then I have an alpha 2, and then I take here next nearest neighbor countries. And then maybe an alpha 3 with third nearest neighbor countries, and so on. So for the reason of time, I will not include the third nearest neighbor coupling in my ansatz. But believe me, if you do, this alpha 3 turns out to be 0 in the end. Okay, so we could, so you only find the terms actually that make up this Maschenbach chain. And what we have to, so I don't consider this in here. So we only have two ansatz terms. I call this guy here H1. I will call this guy here H2. For this Girana method here, we need this correlation matrix. We have two ansatz components, right? So our correlation matrix G is a very simple 2 times 2 matrix. It's looks like this. So we have here H1 squared minus H1 squared. Here we have H1 H2 minus H1 H2. We have the same thing and reverse. And here we have the variance of this H2 component. Right, this 2 times 2 matrix, we need to calculate and diagonalize this correlation matrix. So it turns out, because our state that we study is so simple, right? It's just a product of timers, I can do this analytically. And something that comes in extremely handy is that this singlet state, like the singlet on a timer, I plus 1, is a spin 0 state. It has spin 0 and spin invariant under rotations. So if you, let's say, like you take the alpha component on the side I and some other spin component or the same spin component. If you apply this to psi minus, it's 0. If you do x1 plus x2 applied to psi minus, it gives you 0. This actually means, let's bring this part on the other side. It means that I can do the following: Si alpha psi. Okay. Si alpha tensor identity of I plus 1 applied to psi minus is equal to minus identity on I tensor Si plus 1 alpha psi minus. This property I will kind of use a lot in these calculations. So basically, if I have a spin acting on this psi minus, if I have a timer and a spin acting on this timer, I can shift the spin one side over and pick up a minus. Okay, if you like it pictorially more, let's say this is our timer, okay, and I have a spin acting here. This is equal to minus, the timer with the spin acting. Okay. All right. So let's compute this matrix. what do we need? We need all these things. Let's start with the expectation value of H1. Okay. So this is the expectation value of sum over all sides Si plus 1. And without loss of generality, I will assume that we have an even number of sides. Okay. Now we have, I guess, a state like this, where we have timers here. Okay. So what is this expectation value in that state? It has contributions on the let's say on the timers and between the timers, right? It says I as and so on. So actually, if you have something like this, if you have this, and let's say we act here like the expectation value, I draw it like this, okay, to indicate the expectation value. Like what is the expectation value of this term if it acts between the timers?
Zero.
It's 0, right? Because these timers are completely uncorrelated with each other. What's this? So what I can do now is use this property. I can shift Si plus 1 over by one side. This is minus, then I get a minus, right? I get a minus Si squared, right? I can shift one spin over by one side, then I square this one, and I get a minus, and Si squared is 3, right, with the 3 spin components. It's identity. X squared plus Y squared plus VC squared, they are all, it's identity plus identity plus identity. So this gives you a minus 3. Right, so the expectation value of H1 gives you a minus 3 and half times. Right, so this is minus 3 and halves. Right, H1 is done. Let's maybe do H1 squared. So H1 squared, is the expectation value of sum over all i's and j's, Si plus 1 times Sj plus 1. So actually there are a couple of contributions to consider. So one of them is you have let's draw. So let's say if I and j are equal, yeah, then you can have then you have an si plus 1 squared, right? You can have it either here or you can have it here. Si plus 1 squared. And si plus 1 squared, let me write it out. It's always it's basically, it's xx plus yy plus cc squared, right? So you get, like, this squared is an identity, so you get at least 3 identities, right? From squaring them. And then you get all the cross products, xx, yy, xx times yy, gives you a minus cc. And you get all of them twice. So actually you get minus 2xx minus 2yy minus 2cc. And so you can think about what this is doing. So this one here will give you a 3, right? Because these terms here are again x, what's this, y, correlation functions here. They are 0 because they are uncorrelated. And if it acts here on the bond, then actually you get also this 3, but then also you get like 1 contribution for each of these, because you can again switch, shift over the x and get a minus. So you actually get 3 plus 6 is 9. Okay. And then we also have, like, these are the contributions when I and j are equal. And if I and j are not equal, then you have terms like this, where you have here si plus 1, and here you have si plus 1, right? And they give you both a minus. They give you both a minus 3, I think. What was it? Yeah. So right there. So you shift this over, you get a minus. So this gives you also a 9. Minus 3 times minus 3 is 9. So this h1 squared, to summarize it, and then I'm stopped boring you with these details, is so what do we have? Like, we have this 3, right? We have it n half minus 1 times, because we have n half dimers and n half minus 1 positions between the dimers. Then you have 9 times n half, and this one gives you get for all combinations of dimers, you get a 9, so you have plus 9 n half times n half minus 1. Right, so this is, let's simplify this a bit. This is 3n minus 2 half. This is this thing, and then here you get log that 9n halves. Then you get 9n squared divided by 4. Right, so let's conclude what the variance of what is h1 squared minus h1 squared. So it's this thing, h1, we calculated it somewhere, here it is. Squaring h1 gives you 9n squared over 4, so this goes away with this. So this here is 3n minus 2 over 2. Like this is this now we calculate this matrix elements. This is the first matrix element up here. And the other ones I leave to you. So you can do similar calculations for all these matrix elements. What you find is this matrix. And you know, obviously, looking at this matrix, 1/1/2 is an eigenvector to eigenvalue 0. So here is our Hamiltonian chain. Cool. Let's discuss. So method number 1 was optimization of the variance. Let's do another method. I call it the method of Rare. I definitely spelled the first name wrong. Tao can help me. Do you know these people?
The last two.
The last two.
Just want to ask a question.
Yeah,
So
please.
why does optimize this variance into the ground state?
It doesn't. So it happens to be the case here. I took a state that is the ground state, but by doing this Hamiltonian learning, you have no guarantee that the Hamiltonian that you learn, that the state will eventually be the ground state of the Hamiltonian that you learn. There are some methods which recently came up where you can actually guarantee that there are different techniques of Hamiltonian derivative where you can guarantee that you learn a Hamiltonian which really has the state as a ground state, but not here.
Does this method also include fluctuations? Like Hamiltonian in correlations between
What do you mean by fluctuations?
correlations between other dimensions. Like this is the ground state for this kind of state, but the spectrum can be different for other Hamiltonians with the same ground state. Different Hamiltonians with a different spectrum, but same ground state.
I would say okay. I had here an example where I had two Hamiltonians that have the same ground state. This Heisenberg chain with alternating couplings and this Marshall-Poisson chain. But it actually came again from this fact that the state almost factorizes. It turns out that in general, it's not true. If you take a local Hamiltonian, it's barely the case that you find two local Hamiltonians that have exactly the same ground state. Actually, this G and Rana is a very mathematical paper, but actually they proved, like there are a couple of exceptions to this, frustration-free Hamiltonians. These are Hamiltonians that are sums of projectors. Those are an exception, for instance, because each projector has the state as an eigenstate. But what G and Rana showed is that these exceptions, where this doesn't work, they actually are a set of zero measure in the space of local Hamiltonians, meaning that actually almost all Hamiltonians, you can uniquely recover this local Hamiltonian, which doesn't mean much. These mathematical statements usually don't mean much. These are very formal statements, and in practice it doesn't work. But here in practice, it turns out that this can be done in most cases. So the second method was proposed by these three gentlemen over here, and what they said is the following: like this method can be summarized maybe in one word, and this one word is ITAMP theorem. So you all know the ITAMP theorem. If I compute the time dependence of some observable, of the expectation value of some observable, this is actually equal to minus I expectation value, and then you have the commutator of this observable with your Hamiltonian. And if psi is an eigenstate of the Hamiltonian, the left-hand side is zero. Right? If psi is an eigenstate of the Hamiltonian, it doesn't evolve in time. And all observables are constant in time. So this is zero if psi is an eigenstate. So you have this equation minus I expectation value of this commutator of A with H is equal to zero. Now again, as before, what these people say, let's write down an ansatz for this Hamiltonian. As before, alpha I H I. And plug it in here, let's call it J, use it with the imaginary I. Let's plug it in here, minus I, expectation value, commute, okay. Not already. So it's minus I, and you sum over all sides J. And then you have the expectation value of A Hj. And these coefficients, Cj, goes alpha. Right? So this gives you an equation for, we have a couple of coefficients, by the way. So we have a couple of coefficients Cj that we want to learn, we have now one equation for a lot of coefficients, right? This doesn't work. We need at least as many equations as we have coefficients. Where do these equations come from? What these people propose here is you take multiple observables. You give this A another index K. And now again, this thing here is like a matrix MKJ, right? So you can write this as a matrix equation M times C equals 0. Right? And you again have a matrix equation that you can solve. So you solve this usually by minimizing MC, by minimizing the norm of this vector. Like solve a homogeneous linear equation, or by minimizing the norm squared. The norm squared is actually C transpose M transpose NC. Right, so you construct this matrix M, you compute M transpose M, and then you look for the smallest eigenvalue of this M transpose M. This is how this thing works. And in contrast to this G-Hanan method that we discussed before, this thing actually, one of the advantages here for some experiments at least, is that this here you don't need to measure long range correlation functions. Right, in this previous thing, we had to measure all connected correlation functions between energy densities, and I and J can be far apart from each other. But here you only measure local values. Right, let's see. Don't want to make this too boring. I have slides for it, so let me show you how this works on the slides. Again, also what Francisco said is true for me. Just write an email and you can have these slides. Yeah. So this is what I just explained. This is this Ehrenfest theorem. So how does this work for our example? Actually, since we just have two ansatz components, we just have one equation. Right, so we have one equation, which is this one here, which eventually allows us to fix the ratio between alpha 1 and alpha 2. I mean, something that's of course true about these Hamiltonian learning methods that I'm discussing here is that you can only use them to determine the Hamiltonian up to an overall undetermined scale, right? So if you have a state, it is the eigenstate of H, but of course it's the eigenstate of 10 times H, right? You can this prefactor. You cannot determine. So actually, okay. So let's compute. We need to compute these commutators of some observables with our ansatz components. Question is now, what do you take for these operators here? They call them constraints, right? So this operator, they sort of constrain your equations. And it's somehow a bit tricky in this method to find the constraints that work, but you always get it to work. Okay, it takes some time, but you can always get it to work. Here the issue is that you need to find something that gives non-zero. There is of course the trivial solution where alpha 1 and alpha 2 are both 0. You want to find a non-trivial solution. And you can play around with many observables many times. It is 0, and it has to do with this state here. So this dimer state is a lot of times it's the expectation value is 0, right? You can see that if I have a dimer, like if I have these dimers, like for instance, so here I have my singlets. So actually, if you have here, let's say, two different Paulis, an expectation value of xc on such a dimer, 0, right? Because I can pull the c over onto the x, I get a y, and its expectation value of y in this maximally polarized qubit here is 0. Or, of course, we have seen an x here and x here, 0, right? Also, this kind of stuff is 0. The only thing that's non-zero is if you have the same Pauli, like XX, YY, CC, if you have them on the same dimer, then you get something non-zero. And finding operators such that the commutator of these ansatz terms leads to something like this is not trivial. And I was sitting in front of this in preparation of this lecture for an hour to find the operator that does the job. Actually, what I found is that this does the thing, x, y, z, on 1, 2, 3. So let's see what this does. We need to commute this guy here with sy plus 1. I claim that this is the same thing as the only thing that contributes is this C2, C3, right? Because imagine we have an XX here, right? So let's say an X1, X2. X1, X2 would give you like this X1 it goes away because X1 squared is identity. And Y2, X2 gives you a C2. So you end up with a C2, C3. This is a correlation function here, this is C1, right? And you can work out all the combinations. The only thing that does something is this C2, C3. This actually leads to an X1, X2, and XX on this first timer here. Again, you can pull over the X to the left, and this is minus I. And also for this H2 component, you can do the math. There are now two terms that contribute. You do the math, this gives you a 2I. We are done. Alpha 1 is 2 times alpha 2. There is the machine approach chain. Right. Yes.
What are the main constraints or are you putting on this A operator when you're trying to find A?
In principle, you can take everything. It should not compute with your Hamiltonian, right? You should not take a conserved quantity for this state. But in principle, you could take like random single-qubit operators, right? So just a bunch of them. Actually, you can, this matrix M, you can make it, this matrix M is not square, right? It's like a rectangular. You can make it much, much higher than it is wide. And transpose M will make it square. So you can take much more constraints as you have ansatz terms. And it turns out that sometimes this gains you something, even in the number of measurements, even though you would not expect this to happen.
So maybe I was thinking, like, since you already have access to the state, how do they take that to like sign minus sign minus? Probably this for any general.
Yeah. So this was, I'm trying to emphasize this on my first slide. This is a very good point, Like you have a state, you want to find the parent Hamiltonian of the state. Let's take the projector on that state. But the projector is extremely long. That's kind of the point. And if you restrict it to local Hamiltonians, then you have this method of recovery. Okay. So let me maybe do one of my own things. For this, it is kind of a little bit an extension of this thing. Like this kind of stuff here is like the first order approximation to this idea. It's an extremely simple idea, as you will see. And we did this. I have a paper where I did this kind of stuff for learning entanglement Hamiltonians. And the idea is, if you have in your lab the ability to engineer different Hamiltonians, for instance, a programmable quantum simulator, you maybe have this, or you do kind of digital Hamiltonian simulation. Then you could try to find a Hamiltonian such that if you time evolve the state, it stays unchanged, right? It's also kind of the idea of this here. But here you can time evolve for longer times and go beyond this first order approximation. So actually, what we do here is we time evolve this state with a parametrized Hamiltonian and measure some observables as function of time. At the beginning, if your alphas are not correct and you measure observables as a function of time, they will fluctuate as a function of time. And then what we try to do is we try to tweak these parameters, we try to optimize them such that the system is quiet, right? That all observables are just constant in time. This is what we try to do here. And eventually what this corresponds to is you measure some observable as a function of time, and you can actually apply this time evolution operator on this observable, and what this does is it scrambles the observable in a very complicated way. So you measure extremely complicated observables eventually by doing this. And the reason why we proposed this was, it turns out that with this method you can learn the Hamiltonian by measuring much simpler observables. This O can now be just maybe a sigma c, right? So here you have to measure commutators of observables. So some experiments have problems with that. Think about quantum gas microscope. They can only do shots, you know, and see atoms sitting there. So they are very limited in things that they can measure. And this is something where you can learn the Hamiltonian from these single observables. Right, so actually this was kind of fun. Let's take again our ansatz. And let's do digital trotterized time evolution with these ansatz terms. So you can think we have two gates, you know, one for this first term, one for the other term. This couples nearest neighbors, this couples nearest neighbors. So how could a potential time evolution circuit look like for these operators? So we have these gates here, right? And we need to apply them on the dimers and also between the dimers, right? You see that I also only applied them between the dimers here. The reason is actually, if you apply them on the dimers, the singlet state is an eigenstate of Si plus 1, so this doesn't change. Okay, and what I'm drawing here is just the first trotter time step. We will see that this is okay, because what I want to do is I want to find these coefficients alpha 1, alpha 2, such that the state is unchanged under the time evolution eventually, right? So it needs to be, you know, after this thing, I want to have the same state, right? So how can you see that this Mashunta-Gauss chain does this? Let's use our property that I deleted here, but I put it here again. So actually, if you have Si plus 2, you know, like this kind of orange gate here, which is acting between two timers. Like actually, you can, now with this property, you can shift Si over one side by Si plus 1 to Si plus 1, right? I change just Si to Si plus 1 and get a minus sign. This is this property of the singlet state. And pictorially, what this means is this gate, you can replace it by this one, where you now do not forward but backward time evolution, right? You just shift this over by one side here and change the sign. Let's do this here. You get this circuit. And now you see that alpha 2, if you now want this state to be unchanged, then these two green gates need to undo exactly what the blue gate did. And this means that alpha 2 must be exactly half of alpha 1. Here is your Mashunta question. Okay. How much time do I have left?
Another 10 minutes.
10 minutes, okay. Then for the remaining 10 minutes, so let me close this chapter on learning Hamiltonians from equilibrium states. Actually, let me make one more comment about this method and also about the Lindner method. What we did here is we learned the parent Hamiltonian of a pure state. You can also do this from Gibbs states. If you have a state rho that is e to the minus beta h, you can also learn using this method here, because the same thing applies. You know, like if this Hamiltonian here commutes with rho, right, then none of the observables will change in time. So you can also learn Hamiltonians from Gibbs states, and in this paper from Nathaniel Lindblad et al., they actually proposed this for learning parent Hamiltonians of Gibbs states. This first method I discussed, this G-Rana method with this correlation matrix, does not really work for Gibbs states. Maybe I'm saying something wrong, but I don't. It's not obvious for how you would apply it to Gibbs states because you minimize the variance, right? The variance can be non-zero. You can have non-zero variances in Gibbs states. Okay, so this was this part here, equilibrium states. Let me go to time-evolved states. So this is, like I mentioned this in the beginning, a different type of Hamiltonian learning, which is you have a friend in the lab who time evolves an initial state, and you are allowed, after some time t, do measurements, right? Question is, by looking at the zeros at once, at your measurement outcomes, can you tell your experimental friend with which Hamiltonian he time evolved? You know, can maybe even tell him something that he doesn't know. In this paper here from Lee et al., they proposed to do this by energy conservation. So, of course, for the Hamiltonian, the time evolves the state, energy is conserved, obviously, right? Like the expectation value in the initial state must be the same as the expectation value at time t. H commutes with this thing here. And they propose to use this condition for Hamiltonian learning. Again, same story. Again, you take an ansatz, you plug the ansatz into your Hamiltonian, and you get, again, an equation. All these Hamiltonian learning methods work the same. Again, same problem as here. We have one equations for many unknowns. Doesn't work. We need at least as many equations as we have unknowns. Where do they come from? You have two options. You can measure at different times. You know, you can do measurements at different times. Or you can use different initial states. So these initial states get an index I. So you time evolve from different initial states. And this gives you now a lot of equations. Again, this is a matrix Mij, MC equals 0. You solve it by finding the smallest singular value lambda 1 or the smallest eigenvalue of n transpose n, which is lambda 1 squared. And here you also have this lambda 1, so you can do this, you know, you construct this matrix, and actually this also comes with okay, of course, again, the smallest eigenvector is your optimal Hamiltonian, you know, just look at the smallest eigenvector is the result. And this also comes with a quantifier, like how well this works. If you look at the smallest eigenvalue, it quantifies really the quality of this Hamiltonian reconstruction. Actually, this lambda 1 squared is really, it literally tells you how well energy is conserved for all the initial states. So looking at this smallest eigenvalue, you can tell kind of how this works. Right. One thing that we did, maybe this connects a little bit with what Francisco is talking about, was talking about. So you can characterize digital quantum simulation in Hamiltonian learning. This is something we had a paper about in the past. You know, in digital quantum simulation, you break up the Hamiltonian that you want to simulate into individual bits and pieces, and then this thing is called the Trotter block, and then you approximate your time evolution by exponentials of this Trotter block. This is accurate to order tau squared, and you can interpret this as a Kokail problem. You know, this Trotter block, you can write it as e to the minus IHF tau. This is kind of related to this effective Hamiltonian Francisco was talking about. And this Kokail Hamiltonian is given by this Kokail-Magnus expansion. You know, and this can converge or it cannot converge, depending on the time step tau. So what we applied this Hamiltonian learning to learn a Kokail Hamiltonian in digital quantum simulation. You can ask, why do you want to do this, right? You know sort of what you have in the lab, sort of you know anyway what this Kokail Hamiltonian is by this. But you know, you can have imperfections and noise and couplings to the environment. So experimentalists want to have a scheme, you know, where you sort of characterize this Kokail Hamiltonian. And our idea was to use exactly this Hamiltonian learning that I described before, where you now sort of try to impose energy conservation for this Kokail Hamiltonian. But of course, the energy will not be conserved exactly now, right? For a finite ansatz, because there are these additional terms in this Kokail Hamiltonian. And that this energy is not conserved shows up in a finite value of this smallest eigenvalue of this matrix that you diagonalized. Okay, so our idea was now to look at this lambda1, the smallest eigenvalue of this correlation matrix as a function of the Trotter time step. So we took some Heisenberg model with some field and choose the Trotter decomposition of it. And now you can do this Hamiltonian learning for this Trotterized time evolution. What you do is you write down an ansatz, right? You always start with this ansatz. And if the ansatz is completely insufficient, you know, if the ansatz doesn't even contain enough terms to recover the zero order of this Kokail Hamiltonian, you just see some noise level here. So this thing doesn't work. But if you include now more and more terms, then at some point you see something like this. At some point, the smallest eigenvalue of this matrix starts to scale with the Trotter time step tau, until some point tau star, where it breaks down, where this Kokail Magnus expansion doesn't converge anymore. And actually what we can show is that you can learn this Kokail Hamiltonian order by order. Like what we really can show is that, like, if you start now extending your ansatz, if you start to add more and more HJ terms, more and more ansatz terms, then it suddenly starts to scale like tau squared. And we can show that if this error scales like tau to the k, then your ansatz reconstructs all components of this Kokail Hamiltonian up to order k-1. So you can learn this Kokail Hamiltonian order by order. Okay, so for further discussions, so what I haven't talked about, but what I mentioned is that you can also do this, like, you know, in finite temperature, you can learn this Hamiltonian from Gibbs states. Another thing, I think the question that came up once or twice is how do you guarantee that it's the ground state? Also there, this would be an entire talk on its own. But I'm happy to discuss these kind of things in the break, you know, just approach me. I hope that this stuff was interesting for you. And I think I'm going to stop here. Thank you, guys.
In these quantum simulators, can you also do something like imaginary calculation? Because this variation principle looks like, if you imagine when we solve for variation for the state, we can do an imaginary time evolution. If I can do it to the Hamiltonian, I also will get the Hamiltonian.
You can do this if you have a universal quantum computer, but it's extremely difficult. You know, extremely difficult. It's non-trivial, you know. So you can only do on these quantum devices, you can only do unitaries usually. But there are schemes where you approximate this this imaginary time evolved state by a unitary. So what you do is you propagate in imaginary time a little bit forward, you get a state, and then you try to find a unitary dynamics that approximates this, and you can do this by variational techniques, and you need to measure certain correlation functions. The challenge that comes in here is that you need to measure like matrix elements of unitaries, matrix elements, like you have a psi1, u, psi2, in order to find the parameters that approximate this imaginary time-evolved states, you have to measure stuff like this overlap matrix elements of unitaries. But what experiments have available is maybe the absolute square of these, right? But not really the value itself with real and imaginary part. But this is what you need there. But there are techniques how this can be measured, but it involves a lot of control unitaries and stuff like this. So it can be done. Yeah.
Can we extend these methods to learn open quantum systems like in the Lindbladian?
Yeah. Very good question. I didn't mention this. The answer is yes. Yeah. So you can actually, you raised one of the most important points, which I didn't touch it at all. I forgot about it. You can use so this Ehrenfest theorem. You can integrate it between a time 0 and a final time t, and then again get an equation. And this can be used by measuring like observables as a function of time. You can also use this kind of approach to learn Hamiltonians that govern time dynamics. I use it here for equilibrium states. And this extends to Lindblad dynamics. So you can learn not only Hamiltonian terms, but also jump operators. Yeah, very good question. Thanks for reminding me.
My question just, the question you mentioned, how you guarantee your current as a state synchronous.
Yeah, let's maybe, because people get hungry, let me maybe try to give a 1 minute answer.
Can you repeat the question, sir?
Yeah. The question was, how do you learn a Hamiltonian such that it is guaranteed that the state is the ground state of the Hamiltonian? There has been one interesting paper from the group of Rosario Fazio in Italy. I don't know where exactly, but they call this Hamiltonian reconstruction by our inverse quantum annealing. So you can, by using the adiabatic theorem, like if you have an adiabatic path connecting two states, you could construct such a path from one state. Like if you have a state where you know this state is the ground state of a Hamiltonian, like a trivial state, like this maximally polarized state that I pointed out in the beginning, and you have a path that connects this state to another state, you can actually write down a time-dependent variational principle for this Hamiltonian and can use this to propagate the Hamiltonian forward to the final state. And this is also, I think, experimentally doable and could in principle be reconstructed to learn Hamiltonian such that they have states as ground states. We can discuss this in the break in more detail if you're interested.
No further question for Christian. Thank you both.